Okay, so now we're going to talk about how we can get information out of the M+1, and if there is an M+2 peak, which is only really the case with alkyl halides, what information we can get from that, okay? So again, the first thing that we're going to do is identify our base peak and then our molecular ion peak. The molecular ion peak being really important because that corresponds to the molar mass of the compound, okay? And we said that the molecular ion peak is always going to be just to the left of this other really baby peak, the M+1 peak, okay? This M+1 peak is a result of the presence of carbon-13 in a sample, okay? Something like 98.9% of carbon in this world is carbon-12. However, there is the 1.1% that corresponds to carbon-13. So you will always have sort of that 1% making an influence on your sample, on your spectrum rather. It turns out that you can get a ton of information from this little baby peak. Okay, so let's go in, let's see why that is. You can compare the height of the M+1 to the M peak, and you can get an estimate on the number of carbons that are in each, the number of carbons that are in your sample, all right, in your compound. Again, what we're going to do is we're going to take the M+1 divided by the M+1 peak, the intensity of that M+1 peak, divided by the intensity of the molecular ion peak, and multiply that by 100, and then divide it by 1.1, the abundance of carbon-13 that we would expect, okay? And this will give us an approximation of the number of carbons that are in that molecule. So why is that? Well, because if you think that 1% of all carbon is going to contribute to this M+1 peak, well, the more carbons you have in a molecule, the more likely there is to be an M+1 peak. Well, the more likely your compound is to weigh M+1 compared to M. Okay, so let's just put this into practice to see, given this example here. So notice here my molecular ion is my base peak, so it's at 100. So at the M/Z of 142, we have 100% of our base peak, meaning that it is our base peak. And then at M+1, or at 143, we are at 11% of our base peak. Okay, so we're going to plug this into our formula here. 11 divided by 100 times 100. Move this up. Divide that whole thing by 1.1. So if you punch this into your calculator, what you're going to find is that the approximate number of carbons is 10. All right, so again, it's not always going to be a nice, neat number you might have to round, but it's a lot of the time it's pretty freaking close. It's crazy impressive how well this works. So then if we're going to try to find the molecular formula of this, notice that the question is asking for the molecular formula of a saturated compound. So we don't know if this compound contains oxygen, nitrogen, chlorine, bromine, blah, blah, blah. Let's just assume it doesn't, right? You got to start somewhere. To some extent, this might be, this chapter is very much so at parts going to be a game of guess and check. But we can first assume that it follows this formula here, okay? So if that was the case, it would be C10. Again, that 10 comes from my estimation that I got from the height of my M+1 peak. H would be 22. So then plug this into your compound calculator that you built after the first lecture, and you will find that this compound indeed has an M/Z. The molecular ion would have an M/Z of 142, which is exactly the exactly the M/Z of the molecular ion in this particular example. So just from this information alone, we were able to conclude that this corresponds to this compound here. Okay, so it can be pretty powerful. Let's just do another example. Here we have our molecular ion has an M/Z at 72 with a relative height of 38.3 compared to the base peak. I don't even know what the base peak is. And yet I'm going to show you that we can still get to the molecular formula of this compound. And then the M+1 peak has a relative height of 1.7% of the base peak. So what do we do? 1.7 divided by 38.3. Take that whole thing, multiply by 100, and then divide by 1.1. And what we get is 4.035. We're going to call that 4, right? I mean, if you're doing a molecular formula, it's got to be a nice whole number. Here, my molecular formula is for an unsaturated compound. So again, we don't know where to start, but let's just start with the molecular formula for a simple unsaturated hydrocarbon. That would be CnH2n. So this would be C4H8. If we plug that into our calculator, we would expect that this molecule here, the molecular ion would have an M/Z of 56. Well, clearly that's not what we get, right? However, I know that there aren't any more carbons in there. So I'm just going to play around with the other molecules. Try to throw a nitrogen in there. That would mean that the molecular formula had to be C4H9n. Actually, let's just do another one here. C4H9n. That would be my molecular ion has an M/Z of 71. Notice I probably knew that it wasn't that because that has an odd M/Z or an odd molecular ion mass. It's close though. 72 is the correct one. So now let's go on to the next, which is C4H8O. And indeed, we will find that this molecular ion has a mass of 72, or an M/Z of 72. Okay, so just from that information alone, we can conclude that the formula, the molecular formula for this compound is C4H8O. And there was a little bit of guess and check that we had to do, but that's the procedure. The other way that we could have seen this is we could have taken the 76, subtract, 70, take the 72 and subtract 56, and you would wind up with 16, which corresponds to the mass of that oxygen. So there's a few different ways to do it, but nonetheless, you see the power in this M+1 peak. Probably aside from the mass of the molecular ion, probably the most important part of this whole mass spec stuff. All right, now let's look at the M+2 peak. This is something that only really matters for alkyl halides, okay? So like we said, the big difference between carbon, which has, carbon 12 at an abundance of 98.9 and C13 at an abundance of 1.1, when it comes to the halogens, so for example, chlorine 35 has an abundance of 76%. Chlorine 37 has an abundance of 24%. That's pretty large. That means that no matter what, you're definitely going to get some of that isotope in there somewhere. And notice that the other thing that's really nice is these two isotopes are spaced 2 mass units away, not just 1. So that means that you're not going to confuse it with your M+1 peak, which you're using to figure out the number of carbons. It's going to be an M+2 peak. And so for the case of chlorine, the ratio would be 76 to 24, which is approximately a 3-to-1 ratio. So this isn't going to be something that you do any math for, really, other than when you look at a mass spectrum, you can almost immediately tell whether there's a chlorine atom in there. If you see this big peak all the way to the left, and then 2 units above it, one that's like 1/3 of the sign, that is the signature of a chlorine in your compound, right? Of an alkyl chloride, or in this case, an aryl chloride. But here would be my M peak, my molecular ion. This is my M+2. And again, this one is about 1/3 of the height of my molecular ion. Okay, so again, not anything that you're even really doing quantitatively here, but just by looking at it, when you see this peak, this M+2 that's a third of the size, you're immediately thinking chlorine. Okay, it's one of the easiest things to spot on a mass spec. Second only to when bromine's involved. Okay, again, bromine has a similar phenomenon. The bromine 79 isotope is 51%, and the bromine 81 isotope, again, 2 units apart, is at 49. It's basically a 50-50 distribution of these two isotopes out there in nature. So when you're looking at a mass spec and you see this pair of, all the way to the right of your spectrum, you see these pair of peaks that are exactly 2 units apart, that is the signature of a bromine molecule. Here is my molecular ion. Here is my M+2. And again, these are about 50-50 or 1-to-1. Okay, so again, these are just something that you can see just by looking at it. Now, one interesting thought that we can have here is, well, what happens? So given that chlorine has these 2 isotopes of their 2 abundances, what would happen to the peak of to the molecular ion, the M+2 and the M+4 peaks, if we have a molecule that contains 2 chlorines? So let's just sort of illustrate what we're talking about here. We're just going to like draw a random molecule. Okay. Okay. There are 4 different possibilities that we can have of this molecule here in terms of the chlorine isotope. They can either both have chlorine 35, right? This would be the M+ or the molecular ion peak. We could have our rightmost chlorine be 37, where our leftmost chlorine is 35. And then we could have it the other way around. This is 35. And this is 37. Or they could both be 37, right? These are the 4 different possibilities that we can have for this particular compound. Notice that this would be the M+2 molecular ion, and this would also be the M+2 molecular ion, whereas this guy over here is M+4. Oops. Okay, so let's see if we can't figure out the distribution of these here. So this is kind of back to statistics here, how we would go about calculating this. Well, the chances, if you have a 76% chance of having 1 chlorine 35 atom in your structure, that means that you have a 0.76 times 0.76% chance of having 2 chlorine atoms in your structure, which would correspond to 57, we'll call it 58.58 or 58%. Okay. Now, what about if you had 1 chlorine 35 and 1 chlorine 37? That would correspond to a 0.76 times 0.24% chance, giving you 18.81. We have the same thing over here. 0.24 times 0.76 gives me 1.8, or 0.18, sorry. And then lastly, the chance of us having 2 chlorine 37s is 0.24 times 0.24 equals 0.06. Okay, now since these give the same M over Z, we have to actually sum these up, and you will find that the ratio of M+ to M+2 to M+4, the ratio of these are going to be something like 58 to 36 to 6. Okay, so then we would expect to see those peaks corresponding to those ratios. And again, that's going to be something that's kind of obvious to see, because this peak is about half the size of that peak, plus we have this M over 4. Okay, so again, it's just something that you can kind of easily spot by looking at a mass spectrum.